So this is our second lesson, sort of continuing what we started talking about from lesson 1.1. We're focusing on angle pairs and their relationships with each other. So how many things are in a pair? Two things in a pair, right? A pair of shoes, a pair of earrings, a pair of eyes, whatever. So there's two things in a pair. So angle pairs, we're going to be learning different types of angle pairs. You have to remember that it's always just two angles at a time. The first one we're going to talk about are linear pairs. Okay? I'll define linear pair first, but you already have sort of demonstrated to me that you understand what a linear pair is. Okay, so if you remember the other day when we were doing lesson 1.1, I said measure this angle, and you all measured it, and you came out with 130 degrees. You remember doing that? Okay. Then I said, all right, what does that angle have to be? 50. How did you know that? Okay, because they're both on a straight line or a straight angle, so they have to add up to 180. So this is kind of like, I call it the rainbow, because it kind of goes from one angle through both angles and ends exactly on a line, and so that's a linear pair. And then I said, what would this angle have to be? Also 50. Same reason. Now we have a rainbow that can go this way, right? And that's a line right here. Okay. What would this angle be? 130 again. Again, same reason. So those are linear pairs. So you already kind of know what they are. You just may not have ever called them that before. You may have, actually, in your class last year. They might have mentioned it. So a linear pair is a pair of angles, so two angles that together form a straight angle. So we can draw one by starting with a line and then put like a ray coming off of it. And this is one angle and this is the other angle. And that's a linear pair. Now, notice this is the definition. This is the definition of linear pair. It just describes what the thing looks like. It's just describing it physically. Then we have the linear pair postulate. And the postulate is going to give some like property of linear pairs. And so a linear pair, we know, adds up to 180 degrees. We kind of just know that. But notice that it does not say that in the definition. We need the postulate to state that. Okay, so linear pair postulate says if two angles form a linear pair, then they are, what's the word for when two things add up to 180? Supplementary, right. So, when we look at our diagram, angle 1 is right here. Notice it's not the full right angle, it's just part of it. Angle 1. I want you to fill in right here. Don't say it out loud. Just fill in right here. What other angle goes with angle 1 to form a linear pair? So your answer there should have been angle 3. We can draw this rainbow like this, right? If we went in the other direction, this way, our rainbow, it would take 3 angles to make that complete rainbow, right? And remember, a linear pair can only be 2 angles at a time. So that one, yes, they add up to 180, but they're not considered a linear pair in that direction. Make sense? Yeah. There's not a name for it. The question was, what's the equivalent if you had that situation where there was like 3 that added up to 180? Is there a name for that? And there's actually not a name for that. Somebody else in my other class asked me, what is the name for a pair of angles that together make like a right angle? And there's not a name for that either, and I'm not sure why. In both cases, like this, we could call them supplementary, we could call them adjacent, that's all true, but it's not their definition, and it's not, it's just more things that we kind of notice about it. It's not part of the linear pair postulate. Okay, so an equation we could write then is the measure of angle 1 plus the measure of angle 3 equals 180. If you remember in your homework, we justified, or in our notes the other day, we justified using a reason. If we write an equation using this linear pair concept, our reason would be the linear pair postulate. Okay, so in this one, we are going to, of course, label the diagram first, always. Angle ABD, so measure of angle ABD is this one. That's 20x plus 2. And DBC is 30x minus 22. If you remember, we talked about when you mark angles, like I put this arc here, I want to make sure I put a different marking over here because they're not congruent to each other. If you put the same marking in both angles, it's supposed to signify that they're congruent, that they're the same measure. And these, are different measures. I also want to point out diagrams are not drawn to scale, ever. So never think, oh, gee, I got 10 degrees and it looks like it's 80 degrees. I must be wrong. Don't think that, okay? Because these diagrams are not drawn to scale. You got to just go with it, okay? All right, so what equation could I write here? Ben. Good. All right, then we combine like terms. We get 50x minus 20 equals 180. Add 20 to both sides. Divide by 50. You get x is 4. What's our reason here? Exactly. Linear pair postulate. Perfect. Okay, so sometimes once you get your answer for x, they're going to ask you to find the actual angle measures, and then you're just going to plug your x value back in. So they ask us for the measure of angle ABD. We know that's 20x plus 2, and now we know x is 4 from our answer. We just plug that right in there. So 20 times 4 plus 2, 82. And then we're going to want to do the same thing here. Plug it in. And then you want to sort of check, do these add up to 180? Yes, that's what we want them to do. They do. You might think to yourself, well, I got 82. I don't need to bother plugging in 4 for the other one. I can just say 180 minus 82 and get my answer. That's true if you did it right. The good thing about actually plugging it into both is that if you did make a mistake with your x value, you'd figure that out now, right? Let's say you got x is 40. You accidentally divided and you got 40 instead. But when you plug in 40 here, clearly they're not going to come out supplementary, so you would sort of find that mistake. Okay, you guys try this next one. Label your x is 12. Your equation, when you label your diagram, you add them together and they equal 180 by the linear pair postulate. ABD turned out to be 64 and DBC was 116. Any questions? All right, let's look at the other side. The next special pair of angles are called vertical angles. Have you heard of vertical angles before? Okay, so vertical angles are going to be two angles formed by two intersecting lines that are not adjacent. So they don't share a side. So two angles formed by intersecting lines. If we draw that, we're going to draw one line here and one line here, intersecting lines. And then if I use this angle as one of my angles, and I can't have an adjacent angle to it, that leaves this angle. So those are going to be vertical angles. They're basically, they have the same vertex, but they are not adjacent. So they're kind of across from each other in this intersecting line situation. Now again, if you'll notice, yep, Charlie? Okay, so just like with linear pairs, notice that the definition here of vertical angles just describes what they look like, their physical appearance. But then we have a theorem that goes with that, and that's going to give us some useful relationship. So the vertical angles theorem says if two angles are vertical angles, abbreviation for angles there, right? I use the symbol. If two angles are vertical angles, then they are congruent. Which means they have the same measure. Now, you've heard the word congruent before. What does congruent mean? Tyler? Yeah, it's actually the same exact shape and size. The same exact shape and size. It's like a physical thing, what something looks like. It doesn't have to do with their measures. Congruent really is just describing what they look like. So the symbol for congruence looks like this. See that symbol right there? It's an equal sign with a squiggle over it. That means is congruent to. Now, in this diagram, it says angle 1 and angle what are vertical angles. So here's angle 1. What is the angle that's vertical to angle 1? Yep. 4. Angle 4 is vertical to angle 1. You can see this if you extend the two lines that make angle 1, and then you'll see on the kind of the back door it makes angle 4. So a congruent statement for that fact would be that angle 1 is congruent to angle 4. And the reason there would be the vertical angles theorem. Now, there's a little technicality that we're not really ready to worry much about right now. Eventually we will. But the theorem says that they're congruent, but we're going to write equations, so we just kind of have to make that mental conversion from they're congruent, therefore they're equal. All right? So when we have an example like this, measure of angle 1 is 6x squared minus 7x. We're going to label that 6x squared minus 7x. And angle 3 is 3x squared plus 20. So what equation would we write if these are vertical angles? What equation would we write? Megan? Good. Bless you. Okay. So notice we're not adding things up and equaling them to something like we were with angle addition postulate and linear pair postulate. This time they're vertical angles, so we set them equal to each other. Okay? All right, so I'm going to give you a chance to actually solve this. And yes, it involves factoring. So remember, get everything on one side and set it equal to 0. And then factor. And then you got to check for both solutions and see if they work. Okay, so this one comes out to a factoring where our factored form is x minus 4 and 3x plus 5. And so when we solve, we get this for x. Both work to make positive angle measures, so we have two answers for everything. What's our reason here? Vertical angles theorem. Exactly. Okay, so just a little. Remember from lesson 1.1, we talked about what a plane is. And endless what? Flat surface. Yeah. So I forgot to put in what the notation was for plane in our lesson 1.1 notes, so I squeezed it in here. A plane, an endless flat surface, has lots of points on it. We have to name a plane with more than 2 points, because if we just use 2 points, that could just be a line, and there's lots of planes that go through a line. So we need 3 points to name the plane, but they actually have to be 3 non-collinear points. So that's kind of the trick here. 3 non-collinear points on the plane. We'll name that plane. Now, if you look at this diagram, it's supposed to be showing The yellow part is like the endless flat surface. Clearly it's not endless in this diagram, but you have to imagine that it goes on forever. And then it has a line, TN, which is actually piercing through the plane. I know sometimes it's hard to sort of recognize what's happening in this 3D diagram. So I'm sort of showing it to you here with a paper and a pen going through. This paper is like the yellow part, and then the pen going through is like the TN that's coming up through that plane. Do you kind of see that picture, what's happening there? Okay, so is point T in the plane? No. An N in the plane? No. So to name this plane, can you give me what we could call it? And we do have to write out the word plane. And then what would be an example of 3 points that are in the plane but are non-collinear? 3 points that are in the plane but non-collinear. Non-collinear. Lauren. So, sorry, I couldn't really hear you. R. Right, so pick a different one. R. So R, how about RVS? Right? RVS. Those three are in the plane. They're not all lined up on the same line. Yep. Okay, good question. Why do they have to be non-collinear? Well, if you imagine, if we named this plane RQS, there are infinite planes that can go through RQ and S. Because I could slice it, I'm not going to be very good at drawing this, but I could slice a plane going through that way, right? Kind of like slice it through there. And then I could rotate that just a couple degrees and slice another one, slice another one, slice another one. Almost like a Rolodex. You guys know what a Rolodex is? Yeah, it's like ancient people used to use a Rolodex. Actually, I used to use a Rolodex, but you know, before cell phones, when you had all of your like contacts in your phone, there would be this spin thing. Yeah, it would be like an axis with cards, sort of like index cards that had like 2 hole punches, and you could put them all in a circle around this Rolodex. And then you would just, and it would have like A, B, C, D, and you would kind of spin the thing till it got to the letter of the person's contact you were looking for, and then you would kind of search through the R's. I mean, it could have been in a file, you know, box or something, but the spin made it a little bit easier. So that's kind of what I think of when you think of a line and how many planes can go through it. It's like slice, slice, slice all the way around, like kind of like a Rolodex. Okay, so that's why it has to be non-collinear. Otherwise, you could be naming a plane that isn't drawn, you know. But the other thing that's a little confusing is this letter here. That letter is not next to a point. It's not naming a point. It's naming the entire plane. So typically, this is supposed to be a capital script letter. It should be a little more curvy looking. This P looks pretty plain. But usually it's a little like, if they had named it plain L, it would be, you know, a script L. Anyway, they chose P, which isn't very script looking, but we could also name this by that letter, plain P. I'm trying to make mine a little bit more scripty. Right, plain P, you could call it that. It's kind of a bad looking P, but if a plane has a script letter on it, you could call it by that name. Okay, this box basically recaps the vocabulary and things to know how to do from lessons 1 and 2. So this is basically what your test next week will be on. One thing I want you to add is the word coplanar. Remember, we added it to the notes. We need to add it to this list. Points, lines, planes, angle, vertex, postulate, collinear, intersect or intersection, planes, coplanar. Don't forget that you were supposed to already come into this class knowing these words, and actually you need these for your homework tonight. What does complementary mean? Adds to 90, supplementary adds to 180. Acute is less than 90, obtuse is greater than 90, straight is equals 180. These are the 3 reasons that we learned, right? Sorry, these are the 3 reasons that we learned. And these are the things they go with, right? Angle addition postulate is used with adjacent angles. Linear pair postulate is used when you have a linear pair. Vertical angle theorem obviously is used when you have vertical angles. And then these are some of the skills that you should make sure you know how to do.